Hey there, Data Explorer. Ever feel like lost in a sea of data points, just unsure of what's actually important?
It can definitely feel that way.
Today, we're your guides to navigating that sea with this cool thing called topological data analysis,
Mm,
or TDA for short, right?
that's right.
And we'll be using this research paper you sent over, Bi-Filtration and Stability of TDA Mapper for Point Cloud Data as our compass.
Think of TDA as like creating maps,
Okay.
simplified maps from your data,
Yeah.
highlighting the important connections
Yeah.
and patterns hidden
So
within.
it's like finding those constellations.
Exactly.
Right.
And what's fascinating is this paper focuses on what's called point cloud data, which is
Yeah.
super relevant to a ton of fields, from analyzing customer behavior to like understanding how proteins fold. Basically, any data that can be represented as like a collection of points in some multidimensional space.
Okay, so let's say you have all these data points.
Yeah.
How do you even start to make sense of it? You can't just stare at this jumble of dots and expect to see, anything meaningful.
Right. That's where TDA Mapper comes in.
Okay.
So imagine you're trying to understand this huge, dense forest.
Okay.
Instead of looking at every single tree, you'd want a map, right?
Yeah.
TDA Mapper creates that map.
Okay.
But instead of mountains and valleys, it's showing you clusters of similar data points.
So it groups together data points that share something in common,
Mm,
like customers who buy similar products
precisely.
or proteins with similar structure.
Exactly. And it does this using what's called a filter function.
Okay.
Think of it like a lens that highlights specific features within your data.
Okay.
Depending on what you want to analyze, this function could focus on purchase frequency or energy consumption, really any characteristic that's relevant to your data.
So let's say we're looking at, I don't know, website traffic.
Here.
And our filter function focuses on how long people spend on each page.
Okay.
So would the peaks on our TDA map be the pages where people kind of linger the longest?
Exactly. Those peaks would represent clusters of data points, in this case, website visits, where people spent a significant amount of time, maybe because the content was super engaging or relevant to them.
That's so cool.
Yeah.
You mentioned earlier that TDA Mapper creates a simplified map.
Yeah.
How does it decide what to simplify?
Good question. So TDA Mapper uses something called covers. Imagine like dividing your data based on the range of your filter function.
Okay.
Kind of like creating bins
Got it.
to sort your data. Each bin captures a specific range of values. For example, one bin might be visits lasting 0 to 3 minutes, another 3 to 6 minutes, and so on.
So the bins help organize the data according to the feature we're interested in. But how does it actually group those similar data points together within each bin? That seems like a pretty crucial step.
Absolutely. You're absolutely right. And that's where clustering algorithms come into play.
Okay.
And this particular research paper really digs deep into one called DBS scan.
Okay.
It's like having a detective who can spot patterns and group those data points together in a meaningful way.
A data detective, huh?
Uh-huh.
Okay, so tell me more about this DBS scan. How does it actually help us create these TDA maps?
So imagine you're looking at, like a map of a city at night, right?
Okay.
And it's all lit up. You can kind of see where the clusters of buildings are.
Right.
DB scan works in a similar way. It's finding those like bright spots where data points are densely packed together.
So it's like finding the bustling downtown areas versus those quieter, more spread out suburbs.
Precisely. And it uses two main parameters to do this, epsilon and minpites.
Okay.
So think of epsilon as like the radius around each data point.
Okay.
DBS scan is drawing this imaginary circle of that radius around each point. And minpites is like a kind of like a threshold. It's the minimum number of data points that need to fall within that circle for it to be considered like, in a dense region, a potential downtown area.
So if DBS can sees enough data points, like clustered together within that radius, it's like, okay, this could be a cluster.
Exactly. And what's really neat is that DBS scan doesn't just stop at finding one cluster. It expands outwards from those initial dense regions, connecting nearby clusters that share enough data points. So it's like those downtown areas, kind of like expanding and connecting with other bustling neighborhoods.
That makes sense. But I'm thinking, if we're drawing these circles and connecting clusters, does the order in which we look at the data points actually matter?
That's a very sharp observation. And you're right, it can. Unlike some other clustering methods, DBS scan has this quirk where the order in which it analyzes data can sometimes influence the final clusters, especially when it comes to those those kind of edge cases data points that could be grouped in a couple of different ways?
Edge cases, like what? Give me an example.
Okay. Think about those data points that fall right on the border between two potential clusters. Like imagine you're sorting your sock drawer.
Okay.
Some socks are clearly black, some are white, but then there are those gray ones that could, like,
Yeah, could go either way.
Exactly.
Yeah. I've got a few of those.
Mhm.
So how does DBSCAN deal with those gray socks in the data? Does it just like randomly throw them in one cluster or the other?
Yeah. Well, that's where the order DBSCAN analyzes the data comes in. Depending on which cluster it encounters first, those gray sock data points, we call them free border points, by the way,
Oh, okay.
might get grouped differently.
So our choice of clustering algorithm, in this case DBSCAN, actually has this inherent quirk that could affect our results. That seems, I don't know, a little concerning. Wouldn't that make the insights we get from this whole process less reliable?
Okay, so DBSCAN has this like quirk where those gray sock data points could end up in different clusters depending on like the order we analyze them. So that kind of makes me wonder, how reliable are these TDA maps anyway? Like if small changes in the data or even just the order we look at things can change the map. How can we trust the insights we're getting? That's the million-dollar question, right? And it's why this whole idea of stability is so crucial in TDA. We want to be sure that the patterns we're seeing are like really there, not just, artifacts of how we're analyzing the data.
So we want our maps to be like those trusty old paper maps.
Yeah.
Like consistent no matter what. But with TDA, it seems like we're dealing with something a bit more, I don't know, dynamic.
Exactly. Ideally, we want our TDA maps to be robust to those little variations in data or even, minor tweaks in how we analyze things.
Yeah, that makes sense. We wouldn't want like our whole understanding of something to fall apart just because a few data points shifted around.
Precisely. And that's where this research paper gets really interesting. It dives into how we can actually achieve those stable maps, even with something like DBSCAN, which we know can be a bit sensitive to data order.
Okay, now you've got my attention. How do we make DBSCAN behave? How do we create these stable, reliable maps?
Well, one of the key concepts they explore is something called Bi-Filtration. Remember earlier we talked about those covers and how changing their size or that epsilon parameter in DBSCAN could affect our map.
Yeah, like adjusting the zoom on our map can change how much detail we see.
Exactly. Bifiltration takes that idea a step further. Instead of just looking at what happens when we change one parameter at a time, it's like, let's see what happens when we change two things at once.
So it's like looking at our map from like multiple angles, adjusting the focus and the zoom to see if anything important like changes or stays the same.
Exactly. We're looking for those regions of stability where the overall structure of our map remains consistent, even if we make small tweaks here and there. And what this research shows is that by carefully adjusting those parameters together, like finding the sweet spot for both the bin size and DBSCAN's radius, we can actually get DBSCAN to create stable maps, even with a bit of that, beta wiggle room.
That's pretty impressive. So even though small changes might happen, those major landmarks on our map, those core insights, they stay put.
Exactly. And this isn't just limited to DBSCAN. The paper actually proves this for a whole class of clustering algorithms, including something called single linkage clustering, which you can think of as like a simpler version of DBSCAN. They're all capable of creating stable maps if we use them strategically.
So for our listeners out there, what's the takeaway message here? Why should they care about stable maps?
Because in the real world, data is messy. There's always going to be some level of uncertainty, noise, or just natural variation. Stable maps give us confidence that the patterns and relationships we're seeing are, meaningful and not just flukes. It's the difference between thinking you've discovered a new mountain range and realizing it was just a trick of the light.
That's a great analogy. So stable maps equal more reliable insights, which is what we all want, right? When we're trying to make sense of complex data. This deep dive has been awesome. We've gone from the basics of TDA to understanding how the choices we make can actually affect the maps we create and how to make sure those maps are giving us reliable insights, even with messy real-world data.
It's been a pleasure unpacking this with you.
Thanks for joining us for this deep dive into TDA. We'll catch you next time when we explore another fascinating topic from the world of data and research. Ever feel like you're staring at a jigsaw puzzle, but the pieces are totally scattered, like you can't even find the box top?
Oh, yeah.
That's what it feels like trying to analyze complex data sometimes.
It can be overwhelming, for sure.
But what if I told you there's a tool that can help us uncover that hidden picture? like a way to see the forest and the trees at the same time.
That's what TDA Mapper tries to do. It helps us make sense of these complex data sets. It helps reveal the underlying shape and structure hiding in the data.
It's like taking that jumbled jigsaw puzzle and magically grouping similar pieces together.
Right.
Suddenly the task feels a little less daunting.
Yeah.
And in this deep dive, that's exactly what we're doing, exploring TDA Mapper.
We'll also be looking at one of its key components, DBSCAN clustering.
And we're not just, scratching the surface. We'll also be looking at some of the quirks of DBSCAN.
Absolutely.
And how those quirks might affect how reliable our analysis actually is.
Because let's be honest.
Like sometimes even the coolest tools have their quirks. Right?
Absolutely. But understanding those quirks is what makes us informed users of these tools,
Exactly. So let's get down to it. Imagine a giant scatter plot.
Okay.
Where each point represents a piece of data. That's our starting point.
Okay.
Now, TDA Mapper takes this sea of points and creates a simplified map highlighting clusters and connections.
Think of it like drawing a map of an archipelago.
Okay.
The individual data points are like islands, and then TDA Mapper helps us see how they're grouped together. Which ones are close, which ones are far apart. It gives us a sense of the overall geography of the data.
Okay, I love that analogy.
Okay.
So how does TDA Mapper actually go from a jumbled mess of data points to this beautifully structured archipelago?
It starts with something called a filter function.
Okay.
Imagine looking at our archipelago through different colored lenses.
Oh, right.
Each lens highlights specific features, like the height of the islands, the density of the vegetation, or the presence of beaches.
So we're choosing what aspects of the data we want to focus on.
Yes.
Kind of like applying filters to a photo, almost.
Precisely. Once we've chosen our lens or filter function, we divide the data into overlapping bins.
Okay.
Imagine dividing our archipelago map into a grid with each square representing a bin.
Okay.
We then look at which data points fall into each bin.
So we're grouping islands based on their characteristics as seen through our chosen lens.
Exactly. And here's where clustering comes into play. We use an algorithm, in this case DBSCAN, to group similar data points within each bin. Think of it like grouping together islands that share similar features.
Yep.
Height, vegetation, beaches, within each square of our grid.
So we're starting to see the archipelago emerge.
Yes.
With clusters of islands sharing certain traits.
Yeah.
This DBSCAN clustering sounds intriguing. What makes it unique?
Well, unlike some other clustering methods, DBSCAN is particularly good at two things.
Okay.
Finding clusters of different shapes, so it's not just looking for circles.
Okay.
And handling outliers, data points that don't seem to belong to any particular group.
So it's not just about finding neat little circles of similar data points. That can handle more complex and irregular groupings.
Exactly. DBSCAN is flexible and robust, making it a valuable tool within TDA Mapper. It's like having a map that not only shows us the main island clusters, but also identifies those solitary islands that might be interesting outliers. And it does all of this using two key parameters, epsilon and min-feats.
Okay, I'm ready to dive deeper into those parameters. All right, so we've got our archipelago analogy firmly in place.
Right.
We're using TDA Mapper to group similar data points together, like islands sharing certain features.
Yeah.
And we've just introduced this cool clustering method called DBSCAN.
Right.
But how does DBSCAN actually decide which data points belong together?
Okay.
That's where epsilon and min-feats come in. Right?
You got it.
Okay.
Think of epsilon like a pair of binoculars.
Okay.
With an adjustable zoom. We use epsilon to set the radius around each data point.
Okay.
Essentially defining how far our binoculars can see from that point.
So if we set a large epsilon, our binoculars have a wide field of view, potentially connecting more distant data points.
Exactly.
But if we set a small epsilon, we're focusing in only connecting points that are very close together.
Exactly. It's about defining the neighborhood around each data point.
Okay.
Now, min-feats comes in to tell us how many other points we need to find within that neighborhood to form a cluster.
Okay.
Think of it like a minimum attendance requirement for our island party.
So if we set min-feats to 5, we're saying the party can only happen if we have at least 5 data points, including the host point, within binocular viewing distance.
Exactly.
Makes sense.
Yeah.
But you mentioned earlier that DBSCAN has some quirks.
It does come in. It's true. DBSCAN does have a quirky side.
Okay.
And it all comes down to something called free border points.
Okay.
Imagine an island located right on the border between two squares on our archipelago grid.
Okay, I can picture that.
Okay.
It's kind of caught in no man's land between two potential island groups.
Precisely. Now, here's the thing.
Okay.
Whether that island gets grouped with the islands to its north or the islands to its south can actually depend on the order in which we look at the data.
Wait, really?
Yeah.
The order we analyze the data shouldn't change the outcome, should it?
It seems counterintuitive.
Yeah.
But unfortunately...
That sounds like a recipe for inconsistent results.
And it can be.
Wow.
And it can lead to situations where we adjust our epsilon,
Right.
essentially changing the zoom on our binoculars. Right.
And suddenly, our border island jumps to a different cluster.
That's like zooming in on our map and seeing an island spontaneously teleport to a different part of the archipelago.
Yeah, it can be a little,
So how do we deal with this instability? Should we just accept that DBSCAN is inherently unpredictable?
Not necessarily.
Okay.
Remember how we talked about adjusting both the bin size and epsilon in TDA Mapper?
Yeah.
There's a technique called two interleaving that helps us achieve more stable results, even with these free border points.
So it's about fine-tuning the parameters to minimize those island-hopping surprises. We're essentially stabilizing the archipelago.
Yes.
So we've been talking about these free border points.
Right.
That can make DBSCAN a bit unpredictable.
Yeah.
But you said there's a way to stabilize things.
There is, to make sure our archipelago doesn't rearrange itself every time we adjust our binoculars.
Exactly. It's called 2-delta interleaving.
Okay.
And it sounds way more intimidating than it actually is.
Okay.
It's really not that complicated. So remember how we divide the data into bins?
Yeah.
Those squares on our archipelago map?
Right.
And how we use epsilon to set the viewing radius around each data point?
Yeah, like deciding how far our binoculars can see from each island.
Exactly. Well, 2-delta interleaving essentially says, let's make sure our bins are always at least twice as wide as our epsilon radius.
Okay.
That way, even if a border island jumps ship when we adjust epsilon,
Right.
it's still likely to land within the same bin.
So it's like putting a safety net under those jumpy islands.
Yeah.
No matter how much they hop around, they're still contained within the same general area.
Exactly. We're just making things a little more stable, you know?
Right.
And this technique makes our analysis much more robust. We can be much more confident that the clusters we're seeing reflect real patterns in the data,
right,
and not just artifacts of how we're processing things.
That's reassuring. So we've gone really deep into the mechanics of TDA Mapper and DBSCAN, but let's zoom out for a second.
Okay.
What's the big takeaway for our listeners? Why should they care about all of this?
That's a great question. I think the key takeaway here is that even with powerful tools like TDA Mapper, data analysis is not a simple points and shoot exercise, you know?
Okay.
It's about understanding the strengths and limitations of our tools, being aware of potential quirks, and making informed choices about how we process and interpret the data.
It's like the difference between simply looking at a map and truly understanding the landscape. You need to know how to read the contours, spot the landmarks and navigate the terrain.
Absolutely. And sometimes it's those subtle quirks, those free border points that make us scratch our heads, that actually lead us to a deeper understanding of the data and the tools we use to explore it.
So the next time you encounter a complex data visualization, don't be afraid to ask questions. How was the data processed? What choices were made along the way? And could there be alternative ways of looking at the information?
Those are great things to think about. And by, by embracing curiosity and a critical eye, we can all become more informed consumers and users of data. And who knows, we might even discover some fascinating insights along the way.
Absolutely. And on that note, we'll wrap up this deep dive into TDA Mapper and DBSCAN. Happy exploring, everyone.
Ever feel like you're just drowning in data?
Yeah, like you're lost in the jungle, just trees in every direction.
Exactly. Well, today we're diving into the world of TDA Mapper.
TDA Mapper.
It's a tool that basically helps us swim through that sea of information and helps us discover hidden patterns.
So instead of just seeing a jumbled mess,
we can actually see the paths and the clusters and the outliers.
I like that.
Yeah. So think of it like this. You hand TDA Mapper like a messy pile of your financial transactions.
Okay.
And it spits out this map revealing spending habits you didn't even realize you had.
Like finding constellations in a seemingly random scattering of stars.
Exactly.
Bringing order to the chaos.
And get this, in this deep dive, we're going behind the scenes with an actual research paper called Bi-Filtration and Stability of TDA Mapper for Point Cloud Data.
Okay, before you go any further, that sounds pretty technical.
It does sound technical, but stick with us because we're extracting like the most fascinating bits and explaining why they matter to you and me.
Even if we're not like data scientists.
Exactly.
I'm all for that.
Okay, so let's talk about how this actually works.
Yeah. How does it work?
Imagine looking at an aerial photo of a jungle, right? You see all these trees everywhere.
Right, just a sea of green.
But it's really hard to make sense of it all.
Yeah, you don't see the pathways through it.
Exactly, and that's what TDA Mapper does. It helps us map out that jungle.
So we can see those hidden pathways, those clusters of similar trees,
Mm-hmm.
and even those lone outliers.
Precisely.
Interesting.
So we start with something called a point cloud.
A point cloud.
It's essentially your data visualized as a collection of points. So imagine each of your financial transactions, like a dot on a map.
Okay.
TDA Mapper then uses this thing called a filter function to highlight specific features of that data.
So it's filtering through it to find the stuff we want to look at.
Exactly, like identifying maybe groups of transactions that tend to happen around the same time.
Or if they involve like similar amounts.
Right, exactly.
So it's like changing the lens on a camera
I like that analogy.
to focus on different aspects of the data,
Yeah.
revealing patterns that might have been invisible before.
And by applying different filter functions.
We can like explore different dimensions of the data and uncover a wider range of insights.
It's about seeing all those different facets.
Yeah, getting like a more holistic view.
But this whole stability thing the paper focuses on.
Yeah, what does that even mean? How can a map of my data be unstable?
Exactly. Like I'm picturing like a wonky map.
Right.
That doesn't make any sense.
Yeah, and how does that even happen?
So imagine using a compass to navigate through that jumble.
Okay.
A stable compass is always going to point you in the right direction.
Right, north is north.
Exactly, regardless of like minor tremors, bumps along the way.
Okay.
But what if the slightest disturbance just sent that needle spinning wildly in different directions?
Oh, that wouldn't be good. You'd be totally lost.
That's what we mean by instability in TDA Mapper.
So we want a map that's reliable. It's not going to get thrown off course by like small fluctuations or inconsistencies in the data.
Precisely. And that's where this research paper comes in.
So they're trying to create a more stable map.
Yes, it's about ensuring that the insights we get from TDA Mapper are robust.
And trustworthy.
Not just artifacts of noisy data or random variations.
Okay, so it's like if we're building a bridge,
Okay.
we wouldn't want small changes in the wind to like compromise its structural integrity.
Absolutely. We want that bridge to be stable.
Exactly.
Same goes for our data analysis tools.
We're relying on them to make important decisions.
Exactly. So we need to be confident that those decisions are based on solid ground.
And that's what makes this deep dive so fascinating.
We're going to delve into the nitty-gritty of how researchers are tackling this stability issue.
And what it means for anyone who relies on data to navigate the complexities of their world.
Which is probably all of us these days.
Pretty much everybody, yeah.
So how do we make sure our TDA Mapper compass is reliable and always pointing us in the right direction?
So that's where things get even more interesting. The paper dives into a specific part of TDA Mapper called dbScan.
dbScan.
It's a clustering algorithm,
Okay.
which essentially means it groups data points together based on their similarities.
So it's finding like those patterns in the chaos?
Exactly. Imagine you're looking at a star chart now instead of a jungle.
Okay, I can do that. Trading trees for twinkling lights.
Exactly. Some stars are clustered together in bright constellations.
Right.
Those are your core points. They represent the densest areas of your data where similar events or transactions are clumped together.
So if we were looking at my spending habits, those core points might be all those online purchases I make late at night.
You got it. Then you have stars scattered around the edges of those constellations.
Okay.
Those are your border points.
Yeah.
They're still part of the cluster, but not quite as densely packed. And finally, you have those lone stars floating in the vast emptiness of space. Those are your noise points. They represent outliers in your data.
Those one-off events.
Exactly, the ones that don't really fit into any particular pattern.
I like that. So we've got our constellations, our outskirts, and our lone wolves.
And here's where it gets a little weird.
Okay.
The paper points out that the order in which we feed data into dbScan can actually change which cluster a border point ends up in.
Wait, really?
It's like saying that depending on how we look at the night sky, that star on the edge of Ursa Major might suddenly look like it belongs to Ursa Minor.
The order we look at things changes the outcome. That seems like a pretty big deal.
It is. It's a reminder that even with sophisticated algorithms like dbScan, the results aren't always set in stone. The way we approach the data can have a subtle but significant influence on the patterns we see.
Okay, so how do we account for that? How do we make sure we're not accidentally shifting stars between constellations just by looking at them the wrong way? So how do we make sure we're not accidentally shifting stars between constellations just by looking at them the wrong way?
That's where Bi-Filtration comes in.
Bi-Filtration.
Yeah, it's like having a more sophisticated telescope.
Okay.
That lets us adjust our view of the night sky.
I like that.
Imagine you have 2 dials to play with.
Okay. I'm picturing it, 2 dials on this high-powered telescope. What do they do?
So the first dial controls the bin size.
Bin size.
It's basically like adjusting the zoom on your telescope.
Okay.
You can zoom out to get a wide view of the entire sky, or you can zoom in to focus on a specific constellation in detail.
So it's like changing our perspective from the entire forest to a single tree.
Exactly.
Okay.
And then the second dial controls something called epsilon,
Epsilon.
which is a fancy way of saying how close stars need to be to each other to be considered part of the same cluster.
Okay.
Think of it like adjusting the sensitivity of your telescope.
Okay.
A wider epsilon means you're more likely to group stars together,
Yeah.
even if they're a bit spread out.
So with bifiltration, we're not just looking at the stars from one angle anymore.
Exactly.
We're zooming in and out and adjusting the sensitivity to get a more complete picture.
Right. A more accurate picture of the night sky.
And hopefully a more stable one, too.
And here's the best part. When we use bifiltration, it can lead to something called interleaving.
Interleaving, what's that?
So imagine taking 2 snapshots of the sky with slightly different settings on your telescope.
Okay.
Interleaving means that even though the settings are different, the main constellations still look the same in both pictures.
So it's like those spot the difference games.
Exactly.
But instead of spotting differences, we're confirming that the important stuff hasn't changed.
You got it. Interleaving tells us that our TDA Mapper results are reliable and not just a fluke of how we happen to be looking at the data.
So we're capturing real patterns, not just noise.
Exactly.
That's reassuring.
Right.
But is interleaving like a guaranteed outcome, or are there still some question marks?
It's a great sign it's not like a foolproof guarantee.
Okay.
Achieving stability in TDA Mapper is still an ongoing area of research.
So there's still more to learn.
There's always more to learn and explore.
It's like we've charted a course through part of the galaxy, but there are still vast regions waiting to be discovered.
Exactly, and that's what makes this field so exciting.
There's always a new challenge, a new discovery on the horizon.
Exactly.
This deep dive has been incredible. We've gone from a messy jungle of data to like a telescope that helps us map the stars.
I like it.
But if I had to boil it down, what's the one big takeaway you hope our listener walks away with?
I think the key is to remember that data analysis isn't just about plugging numbers into a machine and blindly trusting the output.
Right.
It's about understanding the tools we're using, the assumptions we're making, and the potential biases that might be influencing our results.
It's about being an active participant in the process.
Exactly.
Asking questions and approaching data with a critical eye.
Absolutely, because ultimately data is just a tool. It's up to us to use it wisely and ethically to make informed decisions that benefit ourselves and the world around us.
And on that note, we'll leave you with this. If even the order in which we analyze data can influence the outcome, what other subtle factors might be shaping our perceptions in ways we don't even realize? Something to ponder the next time you're navigating a sea of information. Thanks for joining us on this deep dive. Until next time, keep exploring, keep questioning, and keep learning. All right, ready to dive in. Today, we're tackling TDA Mapper.
TDA Mapper, yeah, it's a powerful one.
It really is, but I'll admit, it can seem a bit like, I don't know, reading another language if you're not knee-deep in data science every day.
For sure, but that's what we're here for, right? Break it down, plain English.
Exactly. So think of it this way. Imagine trying to navigate a huge city, sprawling, kind of overwhelming.
Okay, I'm with you.
But the map you've got,
Yeah.
total mess, more confusing than helpful. Right?
Oh.
TDA Mapper, it's like that friend who sees you struggling, swoops in and says, hey, I gotcha. Here's a simpler map, just the landmarks you need and how they connect.
Makes it manageable. Yeah, great way to put it. And we're dealing with complex data sets here, often called point cloud data.
Right. Point cloud data. Let's make sure everyone's on the same page with that. Think of it like a star chart.
Each star being.
Exactly. A data point. It's got its own location, its own identity in a way.
And in other fields like medical research, each point could be a patient or their whole medical history.
Right. So much information packed in. And those data points, they can be scattered across so many dimensions, it's hard to even picture.
And that's where TDA Mapper comes in, along with its trusty sidekick, the filter function.
Filter function sounds kind of scary, but is it really just picking what you want to focus on?
Exactly. It's like choosing the right lens for your camera. Mountains or rivers. Yeah. It's your call. What do you want to see?
That clicks. Our source, the paper Bi-Filtration and Stability of TDA Mapper for point cloud data, lays out the whole process step by step, like a roadmap. So we've chosen our focus, our filter. What happens next?
Next, picture laying a grid over your data, like dividing that city we talked about into, say, neighborhoods.
Okay, neighborhoods, got it.
Each square on that grid, that's our bin. And some data points, they might be in multiple bins, just like some neighborhoods blend together.
Fuzzy boundaries. It's always about the fuzzy boundaries.
Exactly. Now, once we have our bins, things get even more interesting because we start grouping similar points within each bin. We call that clustering.
Ah, so it's like sorting, but with data points instead of like socks.
Yeah, exactly. And that's where algorithms like DBS can come in. They're the master sorters, figuring out these clusters based on how close together the data points are. Imagine stars, some clustered in constellations, others more spread out.
Makes sense. So we've gone from this huge mess of data to these neat little groups, all thanks to TDA Mapper. Pretty impressive.
Wait, there's more. TDA Mapper doesn't just give you the groups, it connects them, creating a map or a graph that shows you the relationships.
So each cluster is like a location on that map, and the connections show us the routes between them.
Exactly. It's like drawing a treasure map where the connections lead to hidden patterns in our data.
I love that analogy. And our source actually uses a great visual to explain this, right? They imagine a simple circle as a mysterious island.
Right. And when we run that circle through TDA Mapper, it's like we're charting the island's hidden features, seeing what makes it tick.
Okay, so we've covered the basics of how TDA Mapper works, input the data, choose our focus with the filter function, divide everything into bins, then cluster similar points. But something tells me this is just the first act.
You're reading my mind. Think of this as setting up the game board. Now we get to make it even more powerful by tweaking the parameters.
Like fine-tuning the game for the best experience.
Absolutely. And those tweaks can lead us to even more hidden invites.
Tweaking the parameters, that sounds intriguing. What are we actually adjusting here?
Well, one of the big ones is the size of those bins we talked about, the neighborhoods in our data city.
Ah, so smaller bins would be like zooming in, seeing the finer details within each neighborhood.
Exactly. And larger bins give us the bigger picture, right? The panoramic view.
So it's like having different levels of zoom on a map.
Precisely. And the cool thing is we don't have to just pick one. TDA Mapper lets us explore multiple scales at the same time, something called multi-scale mapper.
Multi-scale, okay, so we get like a set of maps, each with a different level of detail.
And that helps us see which features are the real deal, the ones that persist no matter how zoomed in or out we are.
Makes sense. It's like those satellite images where you can zoom all the way in to see individual houses.
Or zoom out to see the whole continent.
Yeah.
Gives you a much richer understanding than just one viewpoint.
Exactly. And speaking of getting a clearer picture, let's talk more about how those clusters actually take shape. DBS scan, that was the algorithm we mentioned earlier.
Yes. DBS scan. This is where it really shines. Remember density. It's all about how close those data points are to each other.
Like stars clustered in a constellation versus those more scattered across the night sky. But how does DBS scan actually draw the lines? How does it decide where one cluster ends and another begins?
Well, imagine DBS scan is like, I don't know, a city planner, right? They're trying to figure out the different neighborhoods.
Okay, I like that.
Some areas, houses are packed close together. Those are our core points, the heart of each neighborhood. Then you've got the outskirts, the border points, houses a little more spread out, and of course you've got those lone houses out in the sticks.
The outliers, yeah.
Exactly. Those are our noise points, not really belonging to any particular neighborhood.
Great analogy. But you mentioned earlier that the order we feed the data into DBScan actually matters. That's kind of surprising.
It is a bit counterintuitive. You'd think it wouldn't make a difference. But it comes down to those border points, especially the ones we call free border points.
Free border points, those are the ones right on the edge of two different neighborhoods, right?
Exactly. So whether they get assigned to one neighborhood or the other can actually depend on which neighborhood DBScan looked at first.
So it's all about first impressions, even for algorithms.
Exactly. And this sensitivity to order, it highlights something really important about TDA Mapper, about data analysis in general.
Which is?
Even small choices we make can ripple out and have a big impact on the results.
That's a good point. So how do we make sure we're not being misled by those little quirks? How can we be confident the patterns TDA Mapper shows us are legit, not just random noise?
That's where Bi-Filtrations come into play. It's about testing how robust our findings really are.
Okay, how do we do that?
Imagine looking through binoculars. You could adjust the focus to get a clearer view, right?
Yeah.
Bi-Filtrations are similar. We're looking at the data with different parameter settings sort of like adjusting the focus to see if our findings hold up.
So we're basically double-checking our work from different angles.
Exactly. We want to see which features are consistent across different views, because those are the ones we can be most confident about.
Yeah.
It's like that old saying, measure twice, cut once, but for data analysis.
Bi-filtration's like having a buddy double-check your work, make sure you haven't missed anything crucial.
Exactly. And our research paper, they take this idea even further, talking about using perturbation, really
Yeah.
putting TDA Mapper through its paces.
Perturbation. Okay, now that sounds a little, I don't know, ominous. What are we actually perturbing?
Basically, we're introducing these small, controlled changes to the data. Think of it like giving a kaleidoscope a little turn.
Okay, changing the pattern?
Exactly. We want to see if those little shakes, those perturbations, how much they change the maps TDA Mapper creates.
So if the maps go haywire with every little nudge, that's a sign our findings might be a bit, well, fragile.
Right. But if the maps stay pretty much the same, even with the little shakes, that means we've probably found something real, something meaningful, something that holds up.
Makes sense. It's like the difference between, I don't know, a mirage in the desert and an actual oasis.
I like that. And our source, they actually have this great example, figure 8, I think it was, shows how even tiny changes to the data can lead to big changes in the number of clusters you find.
So it's a good reminder, real-world data, it's messy, always going to be those little errors, inconsistencies, things you didn't expect.
Absolutely. Our job as data explorers is to find the methods that can deal with that messiness and still come out with something useful on the other side.
And it sounds like TDA Mapper, especially with these extra tools, the bifiltrations, the perturbation analysis, it's got what it takes to handle that mess. So for those of us about to set off on our own data adventures, what are the key takeaways, the things to remember?
First thing, don't be intimidated by big, complex data sets. TDA Mapper gives you a way to make sense of them. It's like having a map and a compass when you're exploring new territory.
Right. The right tools make all the difference.
And speaking of tools, don't be afraid to experiment. We've talked about filter functions, bin sizes, even different clustering algorithms. It's all about finding what works best for your specific data.
It's about being adaptable, right? Like a good explorer has to be, adjusting to the terrain.
Exactly. No one right answer in data analysis. It's about finding the right questions, the right approaches to uncover the hidden gems in your data.
And just as important, maybe even more so, being a critical thinker. Just because TDA Mapper gives us this amazing map doesn't mean we stop thinking, right?
Absolutely not. That's where those bi-filtrations come in. The perturbation analysis helps us make sure we're seeing the real deal, not getting tricked by illusions in the data.
Right, separating the signal from the noise. So it's like we've got this powerful tool, TDA Mapper, helps us explore these complex data sets. But even more important is how we use it. Right? Being smart, being adaptable, being, I guess, a bit skeptical.
Couldn't have said it better myself. And that actually leads to an interesting question, something to ponder. If even these tiny changes, these perturbations, can have an impact, how can we make our methods even stronger, even more resilient?
That's a challenge, for sure. But also really exciting, right? Pushing the boundaries of what's possible in data analysis. And on that note, I think we've covered a lot of ground today.
We have, from those initial steps, mapping out the data, all the way to these really sophisticated techniques for making sure our insights are solid.
It's been a fascinating journey exploring the world of TDA Mapper. And for anyone listening, remember, the most valuable treasure, it's knowledge. And with the right tools, a good dose of curiosity, and maybe a little bit of skepticism, who knows what incredible discoveries await in those complex data sets just waiting to be explored.
Okay, so have you ever really struggled to get through some really dense research? It's just overwhelming.
Oh, yeah, totally.
It's like trying to find a tiny little needle in a giant haystack.
Definitely. It can feel like you're lost in a maze of information.
Exactly. But what if someone could just give you a map? That's
Yeah.
kind of what we're talking about today, topological data analysis, or TDA. Specifically, this tool called TDA Mapper. It's like X-ray vision for your data.
Yeah. It helps you see those hidden patterns and connections that are really hard to spot otherwise.
It's kind of amazing. And the cool thing is, it's being used in all sorts of fields, like medicine, finance, even social media analysis. We're diving into a paper today called Bi-Filtration and Stability of TDA Mapper for Point Cloud Data. And they use a really simple example to explain how it works, like a circle.
Right. Imagine you have a bunch of data points, and they all kind of form a circle.
Okay, I'm picturing it.
So the first step is to apply a filter. It's kind of like when you zoom in on a map, you're focusing on a specific area, right?
You're filtering out everything else.
Exactly. So in TDA Mapper, this filter helps you highlight specific aspects of your data.
So it's like putting on like those tinted glasses.
Exactly. You're isolating specific colors, specific features in your data. And then TDA Mapper uses what's called a clustering algorithm.
Okay, and clustering, that's basically grouping similar things together, right?
Exactly. Imagine like identifying neighborhoods in a city, similar data points get grouped into the same neighborhood based on how we're filtering the data.
So we filtered our data, we've grouped similar points together. How do we actually get a useful map from this?
Okay, so that's where the mapper part comes in. It takes all those clusters, all those neighborhoods, and creates a simplified visual representation, almost like a network map. You see the main clusters, how they connect those important landmarks.
So instead of just a jumble of dots, we have a road map.
Exactly. You see the hidden structure.
Okay, that makes sense. But, and this is where it gets kind of tricky, imagine using Google Maps, but every time you zoom in or out, the streets rearrange.
Right. That wouldn't be very helpful.
No, not at all. And in TDA Mapper, choosing different parameters can actually lead to different maps.
Yeah, it's a common challenge. How do we make sure we're seeing the most reliable representation of the data?
Right, not just some random version.
Yeah.
How do we know which map is the right one? And this is where it gets even more interesting. We need to talk about filtrations.
Okay, so imagine watching a time lapse of your data, right? Like how it evolves over time.
Okay.
As you adjust the parameters in TDA Mapper, you're essentially seeing how the landscape of your data changes, like different features might appear or disappear.
Ah, I see.
Some features are fleeting, like those small dirt roads on a zoomed-in map, but then you have the major highways.
Right, those are going to stay put no matter what.
Exactly. And in TDA Mapper, those persistent features across different parameters, those are the ones that are most likely to hold those really valuable insights.
It's like finding the signal in all the noise. Those persistent features are telling us something really important about the data.
Yeah, exactly. And that's really what TDA Mapper is all about, right? It's not just finding any patterns. It's about finding the ones that are stable, that are reliable, the ones that give us a true understanding of what's going on.
It's like we're going beyond just the numbers.
Yeah.
And seeing the actual structure of the information itself.
Right, exactly. Think about it this way. Let's say you're a doctor and you're trying to understand, I don't know, a complex disease, right? TDA Mapper could help you analyze all sorts of patient data, symptoms, genetic information, lifestyle factors, all of it. And it could reveal those hidden connections that you might miss with traditional methods.
So instead of just seeing a list of symptoms, you'd see a map of how they all relate to each other.
Exactly. And that could, lead to earlier diagnoses, maybe even new treatment strategies.
Wow. So we've gone from mapping circles to mapping diseases. What else can we do with this?
Oh, I mean, honestly, the possibilities are pretty much endless. I mean, people are using TDA Mapper to analyze everything from climate patterns to, the effectiveness of new drug treatments. It's really remarkable.
It seems like the key is finding those stable insights, those patterns that hold true, even when you have messy or complicated data.
Yeah, absolutely. And that actually reminds me, we talked about those free border points earlier. The data points that could belong to multiple clusters, those can really throw a wrench in the works if we're not careful.
Oh, right. Those indecisive data points.
Yeah.
So how do we make sure they don't mess up our whole map? That's where that Bi-Filtration idea comes in, right, from the research paper.
Exactly. It's like using two filters at the same time. Each one's focusing on a different aspect of the data. It's like using two different lenses to look at something.
Okay, so you're getting a more complete picture that way.
Right. Like a richer, more nuanced understanding of the structure.
Okay, I'm following so far. We're using two filters.
Yeah.
But how does that help with those free border points? How do we make the map more stable?
Well, think of it like this. By adjusting both of those filters at the same time, we're essentially looking at how those clusters evolve under a wider range of conditions. It's like we're stress testing the map.
Ah, okay. So we're making sure those connections are strong and they're not going to fall apart easily.
Exactly. And those patterns that persist, even with the free border points shifting around, those are the insights we can really trust. They're giving us a much more accurate and reliable understanding of the underlying structure of our data.
This is incredible. So we're not just finding patterns, we're finding the patterns that matter, the ones that can actually lead to some real breakthroughs.
Exactly. That's the beauty of TDA Mapper. It lets us go beyond the surface, beyond the noise, and really see the true shape of the information that's hidden within these complex data sets.
So we've really been diving deep into this whole TDA mapper thing, but there's one part we haven't really talked about much yet, and that's DBS scan.
Yeah, DBS scan, it's a pretty crucial part of this whole process. It's the algorithm that's actually doing a lot of the heavy lifting for TDA Mapper.
Okay, so more than just a small detail then. So remind us, like, what makes DBS scan so important here?
Well, imagine you've got this map, right? And it shows you population density. So you can see where those really packed areas are, like cities, and where things are more spread out. DBS scan is kind of like that, but for your data. It can spot those clusters, those groupings, no matter how dense they are.
Okay, so it's not thrown off by outliers or those like less populated areas in the data.
Exactly. It's like a searchlight that can adjust its beam. So it can focus on those really tight clusters, but it can also pick out those significant but more spread out groupings.
Gotcha, gotcha. So how does that play into this whole idea of stability, making sure our maps are reliable?
That's where DBS scan really shines. Remember we were talking about those free border points, those data points that could belong to multiple clusters.
Yeah, the ones that can't seem to make up their minds.
Exactly. Well, DB scan has a way of dealing with those.
Oh, really? How so?
It all comes down to these parameters, epsilon and minpites. Think of it like fine-tuning our searchlight, adjusting the beam to get just the right level of detail.
Okay, so we're telling DBS scan how sensitive it should be to those wishy-washy data points.
Exactly. We can calibrate it to either include those free border points in a cluster or to label them as noise, depending on what gives us the most stable picture of the data.
So it's like we're saying, okay, find the main constellations, but don't get distracted by every little flickering star out there.
Yes, a perfect analogy. And this careful tuning of DBS scan combined with that bi-filtration idea we talked about is how we can achieve those really reliable insights with TDA Mapper. It's about making sure we're seeing the big picture, even with a little bit of uncertainty in the data.
This is amazing stuff. We've covered so much ground, from a simple circle to mapping out all this complex data.
And really, this is just the beginning. As TDA Mapper keeps evolving, who knows what other hidden patterns we'll be able to uncover.
It's like we've got this whole new way of looking at the world, a new set of lenses. Instead of just seeing data, we're understanding the stories behind it.
Exactly. We're seeing those hidden connections that drive everything around us.
Well, I know I've learned a lot today. I hope our listeners have too. It's pretty amazing to think about all those hidden structures out there and the power of TDA Mapper to reveal them.
Absolutely. There's a whole universe of information hidden within complex data. And with these tools, we're just starting to explore it.
Well, that's about all the time we have for today's deep dive. Thanks for joining us on this incredible journey into the world of TDA Mapper.